Hi everyone, this is the first video for section 5.3 on greatest common factors and least common multiples, which we typically just call GCF and LCM. Okay, so the first thing to do is to go through kind of these definitions of GCF. So the definition is the greatest common factor of two or more, right? So this or more could really be in parentheses, two or more natural numbers is the greatest natural number that is a factor of both or all of the natural numbers. Meaning that if we're just finding the GCF of two numbers, it's the greatest natural number that's a factor of both. And if we're finding the GCF of some list of natural numbers, then it's the greatest natural number that's a factor of all of them. And we denote this by this GCF parentheses AB. So that's what a GCF is. And if two numbers have a GCF of 1, we call them relatively prime. So there's two ways to kind of say what I just said. So it's if they have no common factors except for 1. This is just the same thing of saying that GCF of A and B. Well, let me write this better. This is just the same thing as saying that the GCF of A and B is 1. That means that they're relatively prime numbers. Okay, so we want to find these greatest common factors. So the book lists some different ways to do it, so definitely go through and kind of look at that. We're not going to talk about those algorithms specifically. We're just going to kind of go through and do it. So the first one is we want to find the GCF of 18 and 49. So the way that I typically do this is just listing the factors if the numbers are small enough. So I want to go through and list the factors. So what are the factors of 18? Well, we have 1, 2, 3. Then we go to 6, 9, 18. And what are the factors of 49? Well, it's just 1, 7, and 49. Right, because 49 is 7 squared. So whenever the numbers are simple like this, it's really easy to just list out what the factors are. So the greatest common factor, so what are even the common factors? So they obviously both have 1 in common, but that's actually it. The factors of 49 are 7 and 49, and 18 is not divisible by 7. So it's not going to have either of those as factors. So this is going to tell us that the greatest common factor of 18 and 49 is 1. So 18 and 49 are relatively prime. Okay, so that's that one. So now we're going to do an example of finding the GCF of a list of numbers. So we're only going to use 3, and this one tells us to use the prime factorization of a number, of each number. So we'll do just that. So this is kind of a similar concept to listing the factors. We're just listing the factorization. So we know that 12 is 2 times 2 times 3. So this is 2 squared times 3. And we can think about 30. So 30 is 5 times 6 equals 2 times 3 times 6. Oh, sorry, 2 times 3 times 5. We can also think about 75. So 75 is 3 times 25, which is 3 times 5 squared. Okay, so yeah, if you need to show more work to get these factorizations, that's fine, but you don't have to. Right, you can just show these intermediate steps, right? 5 times 6 is 30, and then going to the prime factorization, and that is perfectly fine. Okay, so we now want to find the factors that they have in common. Well, they all have a 3. And the first two have a 2, but not the second one. And the last two have a 5, but not the first one. So this is actually the only factor that they have in common is they all have exactly 1, 3. So that's the greatest common factor. So that tells us that the greatest common factor of 12, 30, and 75 is 3. So the way we got this, we want to use the factors that they share. So for example, if they all had a 3 in common and a 2 in common, then the greatest common factor would be 6, which is 3 times 2. So we just want to use the factors that they share, where the numbers that occur in every prime factorization that we're looking at. Okay, so those are examples for greatest common factor. There's a lot more examples in the book on pages 182. Well, really, 181, 182, and 183. So there should be plenty of examples there to look at finding the greatest common factor. So now we want to talk about the least common multiple. So the least common multiple of two numbers is, you guessed it, the least natural number that is a multiple of both or all. So again, this or more and this or all could kind of be in parentheses, and we could read this as the LCM of two numbers is the least number that's a multiple of both, and the least common multiple of some list of natural numbers is the number that's the smallest number that's a multiple of all of them. And then we notate it just like the GCD as LCM AB. Okay. So again, there's a lot of examples in the book, so we're just going to go through a few. Okay, so there's more than one way to do this. So this first one, okay. So there's more than one way to do this, but the way that I want to do it is by writing out the factorizations again. So we have that 20 is 4 times 5, which is 2 squared. Times 5. 50 is 5 times 10, which is 2 times 5 squared. And 80 is 8 times 10, which 8 is 2 cubed. So remember that then this is going to be 2 to the 4th times 5. Okay. So in order to get the LCM using this factorization, we just pull factors. So this example is going to most closely mirror page 184, where we use these Venn diagrams. So the LCM of 20, 50, and 80. So we need it to be a multiple of all of them. So that means that all of these just have factors, or prime factors, of 2 and 5. So we need to just make sure we have the most of them that there are. So this one has 2 squared. So how many, oh, I write it in red. So how many factors of 2 do these numbers have? So this one has 2, this one has 1, and this one has 4. And so we're going to take the biggest number. So we're going to have 4 factors of 2. And then similarly, we do something similar for factors of 5. So how many factors of 5 there we have? We have 1 here, 2 here, and 1 here. So we're again going to take the biggest one. So this is times 5 squared. So if we multiply these out, 2 to the 4th is 16. 5 squared is 25. And if you cannot do this in the head, you're in your head, we can kind of use that half double thing that we talked about before, or just reassociate. So 16 divided by 4 is 4, and 25 times 4 is 100, which is 400 is the least common multiple of these three numbers. And so we, again, I kind of went kind of quickly through this, but we use the number of factors of each of the numbers. So the number of factors of 2 is, we have 2, 1, and 4, and we always want to pick the biggest one. So in each case, we picked the biggest one, which is 4 and 2. Okay, so we're going to do this again for 36 and 75. So 36 is 4 times 9, which is 2 squared times 3 squared, and 75, we did this in the previous example, so this is 3 times 25, which is 3 times 5 squared. Okay, so we have these prime factorizations. So again, we're going to see how many factors we have of each number. So I actually want to write this so I have some space. So this is going to just rewrite 36 down here. 4 times 9 is 2 squared, 3 squared. So the different prime factors we have are 2, 3, and 5. And instead of writing out the full factors of, I'm just going to write out 2, 3, and 5. Okay, so how many factors of 2 does 75 have? Well, 75 is odd, so it has no factors of 2, whereas 36 has 2 factors of 2. Okay, how many factors of 3 do they have? Well, 75 has 1 factor of 3, 36 has 2 factors of 3. And lastly, how many factors of 5? 75 has 2 factors of 5, and 36 has no factors of 5. So we're going to go through. Remember, we're going to pick the biggest one in all of them. That way, this number is indeed a multiple of 36 and 75. So we can just write this out as LCM 36, 75 is 2 squared, 3 squared, and, oh, sorry. Ooh. Sorry about this. 2 squared times 3 squared times 5 squared, which is 4 times 9 times 25, which is 4 times 25 is 100. So we're going to do 9 times 100 is 900. Okay, so that is how you get the LCM of this one. So you can kind of think about the GCF and the LCM, right, like these sets, like the union and the intersection, where to get the LCM, we took the union of all of the factors, right? We took the greatest number of factors that we had from each of the different numbers, whereas up here with the GCF, we only took the things that they have in common, right? We only took the things that they share. So you can kind of think of this as the intersection of the factors. And you can kind of think of this as the union. Think about this as the union, meaning that if we just kind of listed, I'll do it for this one. So if we just listed all of these factors in a set, so 2, 2, 5, well, actually, is it correct? So we can think about it, right, in this Venn diagram form that they have in the book, that if you kind of do a Venn diagram of all the factors, the LCM will just include all of them. So let's do it actually for, well, we don't have a lot of space. Well, if we do it for 36 and 75, so I'm actually going to erase these and write them a little bit closer. So 3 plus 1, 2, 5 plus 2, 0. Okay, so if we draw a Venn diagram, where we have 36, 75. Sorry, let me make this a little bigger. So we have 36 here and 75 here. So what are their common factors? So their common factors, it's just 3, right? That's the only factor they have in common. Then 75 has a 3 and a 5 and 5. And 36 has a 2 and a 2 and a 3. So in order to get the LCM, 75 should not have a second 3, right? Because it's just 3 and 5 and 5. Okay, so to get the common factors, right, we would just look at this intersection. And the greatest common factor that these two things have is 3. However, if we're trying to get the LCM, we just take all of these factors. So we take the 2 2s, the 2 3s, and the 5, and the 2 5s, and that's how we get the LCM. So this Venn diagram method is really useful to just kind of see what exactly is going on and how to get it. Otherwise, you can use this where you list out how many factors of each thing you have and you just take the biggest one. That'll also work. Okay, so next we want to talk about the Euclidean algorithm. So the Euclidean algorithm is just similar to the fundamental theorem of arithmetic and Goldbach's conjecture. You just need to know what it says. You just really know what it says. It's kind of above what we'll do in this class. We won't deal with things that are kind of as complicated. There is an example in the book on page 183 of how to use the Euclidean algorithm, but again, you mostly just need to know what it says. So what it does say is if we have 2 whole numbers and we divide one of them, then the GCF is the same. So if we have A and B and we divide A by B and we have some remainder, then the greatest common factor of the 2 things is going to be the same as the greatest common factor of what you divided by and the remainder. Yep, so that's what it says. Yeah, and there's a little note that it's used most effectively when repeated until the remainder is 0. Yeah, there's a more common Euclidean algorithm that's used more often in math. I haven't seen this being called the Euclidean algorithm before. Yeah, usually we use it as this, how can we divide, and don't talk about the GCF, but the book wants to apply this to what's relevant in this chapter, which is talking about the GCF. But again, just need to know what this is. The more common thing, or the more important thing right now is this product property of the GCF and the LCM, which says that the product of 2 numbers is the product of their LCF and their GCM. Or sorry, their LCM and their GCF. So this is kind of a nice little property. It makes everything work out kind of nicely. So we want to show that this holds for 24 and 36. So we can say that 24 is 4 times 6, which 4 is 2 squared, and 6 has a 2 and a 3, so this is 2 cubed times 3, and 36 is 4 times 9, which is 2 squared, 3 squared. Okay, so we want to find the GCF and the LCM. So I'm going to do another example using this Venn diagram just because I felt like the other one was kind of small. Okay. So what are the things they both have? Well, they both have 2 2s and a 3. So let me actually make this a bit bigger, this intersection. There we go. So they both have 2 2s and a 3. 24 has an additional 2, and 36 has an additional 3. So from this, remember that we can say that this middle part is the GCF, is the multiplication of this middle part. So the GCF of 24 and 36 is 2 times 2 times 3, which is 12. And the LCM of 24 and 36 is, remember, we take all of everything in the Venn diagram. So this is going to be 2 cubed times 3 squared, which is 8 times 9, which is 72. Okay? And then we just want to verify that. And it may seem kind of hard to you to multiply 12 and 72 and to also multiply 24 and 36. But we can do it just using the factorizations. So 24 times 36. So we take 2 cubed times 3 and 2 squared times 3 squared, which just comes from the prime factorization. And then using the exponent rules that we learned about in chapter 4, we can just rewrite this as 2 to the 5th, 3 to the 4th. And similarly, if we're trying to multiply 12 and 72, we can write this as 2 squared, 3, 2 cubed, 3 squared, as 2 to the 5th. Oh, sorry, that should be 3 cubed. 3 cubed. And they're actually the same. Let me write these threes just a little bit. 2 to the 5th, 3 cubed, and 2 to the 5th, 3 cubed. And we can see that these are indeed the same. So yeah, this is a nice little trick that we can do that just kind of makes things easier. Okay, so I know this was a really long video just because we talked about GCF and LCM all at once, but I hope it wasn't too long and that everything made sense. But like I said, there's a ton of examples in the book that I didn't really talk about and the different ways to do it. But that's all for this part, just using the basic properties of GCF and LCM.